Hello, we continue with lecture number 4 for Math 609. As I mentioned last time, we will discuss scalar products and norms. And we will start with the definition of inner product vector space or a scalar product vector space. That's the same thing. A vector space V over the set of real numbers or the set of complex numbers, together with a mapping that maps V cross V to the real numbers or to the complex numbers and satisfies three conditions, which we will list down, is called an inner product space. What are the three conditions? The first condition is that this mapping that is the inner product mapping has to be linear with respect to the first argument, which means that if we take a vector u and a vector v in the vector space, and we looked at the inner product of lambda u and v, lambda, where lambda u is the first argument of the inner product, then lambda can get out of the inner product, namely the inner product of these vectors is lambda times the inner product of u and v. And if we have a sum of two vectors in the first argument, inner product with w, then it can be split. So we have the inner product of u and w plus the inner product of v and w. The second property, so this is linearity with respect to the first argument. The second property is called the conjugate symmetry, and this means that if I look at the inner product of u and v, I will end up with a number which is the same as if I look at the inner product with v and u and then complex conjugate the resulting number. Let me remind you that if I have a complex number, the complex conjugate of a complex number, a plus ib is equal to a minus ib. And in the case that this mapping maps from v cross v to the real numbers, we do not put the complex conjugation on the top, because complex conjugation of a real number is the same real number. So in this case, we have that uv is equal to vu. Also, what does it mean mapping from v cross v? That means that its argument are two elements from v, u and v. This is, it takes two elements, one of v and the other one an element of v, and maps it into the real numbers or into the complex numbers. That means that the result is either a real number or a complex number. And the third property, so the first property was linearity with respect to the first argument. The second property was conjugate symmetry, which if it maps into the real numbers, we forget about the complex conjugation and then we have a symmetry. And the third condition is positive definiteness. What does it mean? Then if we take an element u from the vector space and we look at the inner product of u and u, we will end up with a number that is strictly bigger than 0 if u is not the 0 element, which is the same as saying that u and u, the inner product of u with itself is bigger than or equal to 0, and the inner product of u with itself is 0, implies that u is the 0th element. So to summarize, V here is an abstract vector space. And in this abstract vector space, we consider a mapping that satisfies these three conditions. Then this mapping is called an inner product, and the vector space is called an inner product space over the reals, or if the mapping is into R, or over the complex numbers if the mappings is into C. The next definition is the following. If we have the vector space V, and we look at two elements U and V, we say that they are orthogonal if their inner product is equal to 0, which is also, we can write that U is perpendicular to V or orthogonal to V. And if we have a set of non-zero vectors in V, let's say S consists of an elements S1, S2, and so on as K, then this set is called orthogonal. So each of those is different from 0. Is called orthogonal if its elements are pairwise orthogonal. What does that mean? That if I take one element and another element, then this inner product is equal to 0 every time when I choose different elements. So every time when I is different from J, Si inner product with Sj is equal to 0. Now, another remark is that if we have vectors in an orthogonal set, which is vectors that are non-zero and that are pairwise orthogonal, then these vectors are linearly independent. And we can prove this little claim. So let's say we have vectors in S, let's say V1, V2, and so on, Vn, are set of vectors that set is orthogonal set, which means that all the vectors are different from 0, I equals from 1 to n. And also this means that Vi orthogonal Vj inner product with Vj is equal to 0 when I is different from j. And what we want to show is we want to show that these vectors are linearly independent. And to show that they're linearly independent, we start with the following. We start with a linear combination C1V1 plus C2V2 plus and so on plus CnVn is equal to 0, where Ci's are scalars and where Vi's are the vectors from here. And what we want to show that every time we have this relation for some scalar Ci, then these scalars will be 0. If this is true, then the set of vectors V1 to Vn is linearly independent. And how do we do that? We look at this equation and we multiply both sides of the equation scalarly by the vector Vi. So what does that mean? We take the right-hand side, C1 V1 plus and so on plus Ci Vi plus and so on plus Cn Vn. Inner product with Vi is equal to 0 in inner product with Vi because this element here is equal to 0. So if we use the property of inner product, namely that it is linear with respect to the first argument, we can split the sum and we can pull out all the constants out. And when all the scalars out, and when we do that, we will end up that the left-hand side of this equation is C1 V1 Vi plus and so on Ci Vi Vi plus Cn Vn Vi is equal to, we can view this 0 as the 0th element in the inner, the 0th element in the vector space. We can view it as the number 0 times any element. And then if we use the linearity, we can pull the 0 out. And if we pull the 0 out, we'll have 0 times something, which will be equal to 0. So the inner product of 0th vector, of 0th element in the vector space with any vector is equal to 0. Now we use the fact that the elements in the set are pairwise orthogonal, and therefore this will be equal to 0 this will be equal to 0. So all these inner products in this sum will be equal to 0, except this one. And this one will be different from 0 because of property number 3. We see here that the inner product is bigger of an element with itself is bigger than 0 if this element is non-zero. And this element is non-zero because it belongs to the orthogonal set, and therefore, by definition, all the elements in the orthogonal set are non-zero. And so we have that the number Ci times something that is different from 0 is equal to 0, which can happen only when Ci is equal to 0. When we multiply here the scalarly by Vi, Vi was any Vi. This means the index I was any number between 1 and n. So we can do that for all I. And therefore, Ci is equal to 0 for I from 1 to n. And thus we show that if we have a linear combination of the vectors from the orthogonal set to be equal to 0, then we ended up that all the scalars in this linear combination must be 0, and therefore the orthogonal set is a set of linearly independent vectors. So usually when one works with orthogonality and orthogonal sets, the main trick is to, once we have some relation, to multiply both sides of that relation scalarly with a chosen element, and then use the fact that this element is orthogonal to something. Now we continue further to show an examples of a mapping that is an inner product. So our first example is the vector space V, which will be the vector space of consists of all n tuples, x1, x2, and so on, xn, whose coordinates are real numbers. We know that this is a vector space because we can define sum of two elements. Sum of two n tuples is an n tuple with coordinates, the sum of the corresponding coordinates, and we multiply a scalar by an n tuple by multiplying this scalar by any of by all the coordinates in this n tuple. So in these two operations, this set, the set Rn, satisfies all the axioms of the vector space with respect to these two operations. And then one can show that the mapping, which to any two n tuples x and y assigns a number by the formula x1 y1 plus x2 y2 and so on plus xn yn, that this mapping is in fact a scalar product because it satisfies all these conditions 1, 2, and 3 that an inner product is supposed to satisfy. Of course, when we say here that this is an example, this needs a proof. So one has to sit down and look at the definition of this mapping, which is a mapping from Rn cross Rn to the real numbers, and show that this mapping defined through this formula satisfies condition 1, condition 2, and condition 3 in the definition of a linear of a scalar product of a scalar space inner product space, and therefore it is a scalar product. Another definition, another example is when the vector space V is the set of all n tuples whose coordinates are complex numbers. And then we can define an inner product between any two elements of Cn through this formula xi bar times yi. And one also can show that this formula defines a mapping that satisfies conditions 1, conditions 2, and condition 3 of the conditions that are necessary for something to be an inner product space. Now, if we look at the space, for example, R2, and if we look at the vectors 1, 1, and minus 1, 1, and if we look at the inner product of these two vectors, this is the inner product that is defined right here and that you know from probably calculus, and then we know how to compute the inner product. The first coordinate times the first of the first one times the first coordinate of the second n-tuple. Here it is a pair, and plus the second coordinate of the first one times the second coordinate of the second one. So we have 1 times minus 1 plus 1 times 1 is equal to 0, and therefore this n-tuple, this pair 1, 1 is orthogonal to the pair minus 1, 1. And if we look on the plane, if we look at R2, and we draw the tuples, the pairs 1, 1. So here is 1, 1. This is a vector with coordinates 1, 1. And then we look at minus 1, 1, minus 1, 1. So we will see that this angle is a right angle. Another example is, for example, the vectors 1, 0 and 0, 1. These are the standard basis for R2. So this is the vector E1 that is on the x-axis with coordinates 1 and 0, and then 0, 1 is the vector E2. And we know that these two vectors, so this is E1, 0, and then 1, and this is 0, 1, and then 0, and then the vector E2, which is 0 and then 1, and we know that these two vectors are perpendicular. So in this particular case, it coincides with our intuition and of our understanding of what orthogonality is from our geometry class, for example. Now, another case that we will consider is the following. The vector space in this case will be the set of, will be denoted by L2AB. It will be always with a letter L, and then the index here will be different. This index will show up right here in the power. This corresponds to the power, and this is the AB means an interval. This interval can be open, closed, can be finite or infinite. So L2AB is the set of all measurable functions that are defined on the interval AB and have complex values, or they can have real values, such that this Lebesgue integral of absolute value of f of x squared dx over the interval AB is finite. And then one can define the inner product over this set. As I mentioned before, when we say the set of all functions, actually every element here is an equivalence class. It consists of a set of functions that differ from each other on a set of measure 0, and we defined inner product between every two elements of this space by the formula integral from a to b of f of x, and then the complex conjugate of the g of x dx. Now, if the functions are not complex valued but real valued, then we forget about this complex conjugation sign. And an example of two functions that are orthogonal is the following. Let's consider the space L2 of -1, 1. So what is this set? This is the set of all functions or equivalence classes that are defined on the interval -1, 1. Take complex values, and for which this integral from -1 to 1 is less than infinity. So integral, they are measurable too, from -1 to 1 of absolute value of f of x squared dx is finite. And we would like to find two elements at least, or we'll give an example of two elements that are orthogonal. They have to be functions. For example, if I take the function f of x, which is equal to x squared minus 1 over 3, this is a polynomial of degree 2 as a function. It is defined on the whole real line, and particularly I can look at the restriction of this function on the interval -1, 1. And also let's look at the function g of x, which is the identity, the constant function 1. It is also defined on the whole real line. I can look at this restriction on the interval -1, 1. And the question is, are those two functions orthogonal to each other? In order to do that, we have to show that the inner product of f and g is equal to 0. And we will have to look at the definition of what inner product is in this particular case. So in this particular case, this is what inner product is. So we have to show that integral from -1 to 1 of the first function, which is x squared minus 1 over 3, times the second function complex conjugate, but my function is real value, so I do not need the complex conjugation, dx, whether this is equal to 0. Well, first, let us observe that when we integrate the from -1 to 1 of some function, and this function is even function. So if we integrate an even function over a symmetric interval, that means interval from -a to a, this is twice integral from 0 to 1 of this function f of x dx, provided that if f is even. What does it mean that the function is even? That means that f of x is equal to f of x is equal to f of minus x. So apparently this function here is even because all the powers of x that participate here are even powers. So this integral then will be equal to twice integral from 0 to 1 of x squared minus 1/3 dx. And if we use the formulas for integration, so this will be 1/3 x to power 3 minus 1/3 x, and this between 0 and 1. And so this will be 2, 1/3 minus 1/3, and then minus 0. So this will be equal to 0. So indeed, we ended up with two functions, x to the third minus 1, x squared, sorry, x squared minus 1/3 is the first function, and 1 is the second function. And we showed that these two functions are orthogonal on the interval -1, 1. Since they are also polynomials, x squared minus 1/3 is polynomial of degree 2. The constant 1 is a polynomial of degree 0. We have an example of two polynomials that are orthogonal on the interval -1, 1. If we continue further, the next definition and the next term that we're going to introduce is a norm. So again, we have an abstract vector space over the real numbers or over the complex numbers. And a norm on this abstract vector space is any mapping which is a real valued function that is from V to R. Actually, it is to R plus, because it satisfies the following three conditions. So any mapping from V to R plus means the set of all real numbers that are bigger than or equal to 0, that satisfies the following three conditions. The first condition is that when you apply this function to any element of the space, you end up with a number that is bigger than or equal to 0. And this, you end up with 0 only if the element that you apply to from the vector space is the 0th element. The second condition is that it's called absolute homogeneity, and this means that if you look at the norm of a multiple of a scalar times u, then the scalar can get out, but with an absolute value. That's why it's called absolute homogeneity, times the norm of u. And then the third inequality is the triangle inequality, that the norm of u plus v is less than or equal to the norm of u plus the norm of v. So once again, any abstract vector space, any abstract function that to every element of the vector space assigns some number, and this assignment satisfies these three conditions, is called a norm. Why do we introduce a norm? If we look at the case when the set V consists of all real numbers, and we look at the function, the absolute value of a number. We know that the absolute value of a number is equal to, is defined the following way. It is a number if A is bigger than or equal to 0, and it is minus a number if A is less than 0. And the idea of the absolute value, it tells us basically the magnitude by how far away is 1 from 0. Or if I have two numbers A and B, and if I look at A minus B and I look at the absolute value of A minus B, that tells me how much is the difference between A and B, by how much those two numbers A and B are apart. Now, so the absolute value of A tells me the magnitude of the number A, the real number A. Now, the question is, if we are in a very abstract case, in the case when V is an element of an abstract vector space, then how do we measure a magnitude of a vector? We measure a magnitude of a vector by the norm of this vector. And similarly as here, we measure the magnitude of the difference between how far apart are two vectors by measuring the norm of the difference of these two vectors. Now, if we go back to the absolute value, the question is it true that the absolute value is in fact a norm for the vector space R? Well, it is easy to check. The absolute value of every number is bigger than or equal to 0, as we know, and the absolute value of 0, absolute value of a number is 0 only if this number is 0. So the first condition is satisfied. The second condition, the absolute value of a number times A. We know that the absolute value of a product of two numbers is the product of the absolute value. So indeed, we have the second property, the absolute homogeneity, because we can pull out the lambda out via absolute value. And the third, and therefore the second condition is satisfied, and the third condition is satisfied too, because we know that the triangle inequality holds, namely if we have two numbers A and B, then absolute value of A plus B is less than or equal to absolute value of A plus absolute value of B. So also the triangle inequality will hold. So the conclusion is that if we look at the vector space of real numbers, and if we look at the function absolute value, which to every real number assigns the absolute value of this real number, then this function satisfies all the conditions necessary for a mapping to be a norm, and therefore it is a norm. So, as I mentioned a few minutes ago, people needed to expand the notion of an absolute value of a number in order to measure magnitudes of elements of vector spaces, or in order to measure how far apart from each other are two elements of a vector space. And therefore, they introduce the abstract mapping called a norm. And now we have this abstract mapping, and through the norm, we can define various notions. Here I put it maybe some down. Yeah, norms define different notions of length or different notions of magnitude. Now let's go back. Once we have a norm that we said it's an abstract abstract mapping with which we define length or magnitude of a vector, then we can talk about how two vectors are close to each other, or we can discuss various concepts that we discuss or that we deal with when we discuss numbers. But before that, if we have an inner product, so if V is an inner product space and it has inner product, so it is given by some abstract function which to every tuple of elements from V assigns the number, which is the so for U cross V assigns the number UV, which is the inner product of these two elements. If we look at the mapping, which to every element U assigns the inner product of U with itself, and then we take a square root of that number, one can show that this mapping is in fact a norm. So once again, if we have a vector space V, if we have an inner product defined on the vector space V, and if we take to every element U, we assign the inner product of U with itself, and we take a square root of that number, then we will have a mapping that to every element U of V assigns a non-negative number. One can show that this mapping satisfies conditions 1, 2, and 3 that are conditions of a norm. Basically, this will follow from the conditions that are the conditions for inner product. And once show that this mapping here satisfies the conditions of a norm, then we have a norm. And therefore, every scalar product determines a norm. So if a vector space is given, and if an inner product in this vector space is given, that means we will have a norm on this vector space, and we can measure magnitude of elements in this vector space. We can measure distance between two elements of the vector space. Now, in one vector space, there may be more than one norms, as we will see. Now, once we have a norm and we have the tool to measure magnitude, we can expand our definition of orthogonal set Remember that a set of non-zero vectors was called orthogonal if every two vectors are orthogonal to each other. Now we can put additional restriction on this set, and we can require that every element from this set has norm 1. And if this is the case, then the set is called orthonormal set. For example, if we look at the set 1, 0 and 0, 1, we see here that, so this is the vector E1 and this is the vector E2, which are two elements in R2. We see here that those elements are orthogonal because 1 times 0 is 0, 0 times 1 is 0. When we add them, these zeros will end up with 0. So their inner product of E1 and E2 is equal to 0. And moreover, the the norm of E1 is equal to 1, and the norm of E2 is equal to 1 as well. Why this is the case? Because if we look at the norm of E1, this is the norm that is induced by the scalar product. So the norm of E1 is equal to the inner product of E1 with itself, 2 power a half. So we follow this definition. The inner norm of the scalar product of E1 with itself, this is 1 times 1 plus 0 times 0. So this will be 1 to power 1/2 is equal to 1. And in the same way, the inner product, the norm of E2, this is the norm induced by the scalar product, is E2 to power 1/2. And therefore, it will be 0 times 0 plus 1 times 1, which will be 1 to power 1/2, which will be 1. So the set of vectors E1 and E2, this is an orthonormal set. We can get another example of an orthonormal set. If we look at our example for L2, of minus 1, 1. And we looked at the function f, which was x squared minus 1 over 3. And we look at the function g, which is 1. We showed before that they are orthogonal. Now the question is whether they are orthonormal. Let's look at the norm of g with in this space L2 minus 1, 1. So by definition, this is the inner product of g with itself. So this is the integral from minus 1 to 1 of 1 times 1, and this raised to power 1/2. So this will be twice integral from 0 to 1 of 1 dx, and this raised to power 1/2. Which is twice times x between 0 and 1, which is 2. So this is square root of 2. So 1 is not, the function g is not orthogonal, but we can make it orthogonal. The norm of g is 1 over square root of 2. And let's see what will be the norm of the function f. The norm of f is the inner product of f with itself to power 1/2. Now, by definition of the inner product in this space, this is integral from minus 1 to 1 of x squared minus 1/3. And then this multiplied by x squared minus 1/3. So this whole thing multiplied by raised to power 1/2. And what we can do here, this is integral from minus 1 to 1. So this is x squared minus 1/3, everything squared. So this will be x to power 4. And then will be minus 2 over 3x squared. And then it will be plus 1 over 9. And this dx, and this raised to power 1/2. And this way one can find with next computation, whatever number is, this will be the norm of this function. Now, if we have an element for the general case, if we have an element U, so let me put it here. If U is an element that is non-zero element of the vector space V, and if the norm of U is something, if U is different from zero, then the norm will be bigger than zero. Then how are we going to to create an element that is related to U, but has norm 1? So if we look at the element 1 over the norm of U, which is a number, times U. This is also an element of the vector space. So let's consider this element and denote it by V. What will be then the norm of V? The norm of V will be equal to the norm of, by definition, this is 1 over the norm of U times U. We close the norm. Now this here is a number. This number can get out with absolute value, but because the norm is bigger than or equal to 0, here we do not need an absolute value. So this is 1 over the norm of U. And then whatever is left inside is the norm of U. And therefore, this norm and this norm of U will cancel out. And as a result, we will have 1. So the element V will have norm 1, which means the following. If an element is given to us, we always can normalize it. So we can create from this element an element with norm 1 the following way. We look at this element and we divide it by, or think of it multiplying by 1 over the norm of U, or think of it dividing it by the norm of U. This is a new element now in the space V, but this element has norm 1. Now, let's continue further. When we talk about all those norms, then an important object is something called closed unit ball. Closed unit ball, this is the set of all elements in the space, in the vector space, whose norm is less than or equal to 1. Now, as I mentioned before, on one vector space, we can have more than one norms. So if we have 2 norms, N1 and N2 on a vector space, we say that these 2 norms are equivalent if there are positive constants C1 and C2, such that if we look at the N1 norm of the element X, it is within C1 and 2 norm of the element X and C2 and 2 norm of the element X. So it's bounded from below and from the above with a constant times the N2 norm of the element X. And this is true for all elements X in the vector space. And the constant C1 and C2 do not depend on X. They are once and for all. And this inequality here holds for every element X in the vector space. Now, an important theorem which is used quite some time is the following, that if V is a finite dimensional vector space, then any 2 norms on a finite dimensional vector space are equivalent. The constants in this equivalence, which are the constants C1 and C2, may depend on the dimension of the space, N. However, they exist, and it is and they can, the constants may be big, therefore if they depend on the dimension of the space V, nevertheless they are absolute constants, and they do not depend on the particular element that X that is here in the inequality. So now we will consider several examples of norms. The same way as we considered examples about inner product vector spaces, These need proofs that the mappings that we will discuss below are norms. For example, if we look at the n tuples X consisting of all vectors in Cn, if we look at vector X in Cn, whose coordinates are complex numbers, then to every vector X, we can associate a number via the following formula. We look at the coordinates of X. Let me write it here as a vector column, X1 and so on, Xn. So this is the vector X. And then we look at the first coordinate and look at its absolute value. The first coordinate is a complex number. Plus we look at the second coordinate, we add its absolute value, plus and so on. We look at the last coordinate, we look at its absolute value. We add the absolute value of all the coordinates. And this is a number. This number is bigger than or equal to 0. And one can show that this number here satisfies all the conditions 1, 2, and 3 of a mapping to be a norm. And therefore, this mapping defines a norm. This norm is called L1 norm, and it is denoted either this way with a subscript here 1 or subscript 1 L1N. 1 means that the power here of, is 1 of the axis of the absolute value of the coordinates, and n stands for the fact that this the original vector was a vector from Cn, was n-dimensional. Another example of a norm, and it is called the L1 norm. Now, one can ask the question, what is the L1 norm to compute an L1 norm of a number, of a vector? For example, let's look at the vector -1, 1. What will be the L1 norm of this vector? This is the absolute value of -1 plus the absolute value of 1. So the L1 norm of this vector is equal to 2. If we look at the vector 1, 0, the L1 norm of this vector is absolute value of 1 plus absolute value of 0, which is equal to 1. So in this case, we see that the L1 norm is the same as the length of this vector as we know it, the Euclidean length. And it is not equal to the length of this vector, because if we look at the Euclidean length of this vector, this is what? Square root of -1 squared plus 1 squared, which is equal to square root of 2. So the Euclidean length, which you have are familiar with using the Pythagorean theorem, the length of this vector is square root of 2, but the magnitude of this vector with respect to this norm, the L1 norm, is 2. So you see that for the space Rn, the same vector can have different magnitudes depending on what norm we are measuring its magnitude, with respect to which norm we are measuring its magnitude. Now, we can talk about the L2 norm, which is the usual norm that you know from calculus, or maybe even from geometry, that if you have a vector x1, x2, and so on, xn, let's talk about real vector with real components, then we know that the length of this vector, the magnitude of this vector, this is the sum of the absolute values of its coordinate squared. I is equal from 1 to n. Here we may not put the absolute value because we have the square, and then we take a square root. So if we look at the geometric interpretation, if this is the in R2, if this is a vector x1, x2, and then the magnitude is basically the distance of this point to the center of the coordinate system. This is the Euclidean distance of, this is the length of this line segment. Now, what is important here for the L2 norm is that, first of all, it coincides with the norm that you know so far as a distance from a point to the center of the coordinate system, or the length of the line segment. And also what one can see is that this norm, in fact, the L2 norm, is the norm that is generated by the inner product. Remember here that whenever we have an inner product, we generate a norm that is associated to this inner product via this formula. So the Euclidean norm is in fact the norm that is associated to this inner product, because it is the inner product of X with itself and then taking the square root. In general, one can define the LP norm for P between 1 and infinity, and an LP norm of a vector X in the space Cn or Rn, where X is n tuple with either real entries or complex entries, is defined the following way. We look at the coordinates. So we have x1, x2, and so on, xn are the coordinates. We look at the absolute value of the first coordinate, raise it to power p, plus and so on the absolute value of the last coordinate, raise it to power p, and then the whole thing raised to power 1 over p. So one has to show that this mapping, which to every vector x in Cn or Rn assigns this number, that this mapping satisfies conditions 1, 2, and 3 of a mapping to be a norm, and therefore prove that this is a norm. You see here that in the case when p is equal to 1, we have the sum of the absolute values raised to power 1, and therefore we will recover the L1 norm. When p is equal to 2, we will have this case here, and therefore we will recover the L2 norm. And finally, for the case of a vector space being Cn or being Rn, we talk about the Ln infinity norm. And what is the Ln infinity norm of a vector? So we look at the vector with its coordinate x1 to xn. We look at the absolute values of its components, and we take the maximum of all these absolute values. And this is again a norm. We are not going to show for any of those that we mentioned that is a norm except this one. And we will prove it right now. So the first condition for a norm, if we go back and check what was the first condition for a norm, we want something to be bigger than or equal to 0, and equal to 0 if and only if it is 0. So clearly, if we have a maximum, so let me write it here because I will have more room. So we want to show that the mapping which to every element x in, let's do it Rn, the same similar will be in Cn. The mapping that for every n tuple in Rn to every tuple in Rn associates a number which is denoted by this and is given by definition maximum of the absolute value of the coordinates when I is equal from 1 to n. Now clearly this is bigger than or equal to 0 as a mapping as maximum of non-negative numbers. And this is equal to 0 if and only if a maximum of non-negative numbers is 0 if and only if all the elements are 0. So if and only if xi is equal to 0 for every I, which is if and only if xi is equal to 0 which is if and only if the vector x is the zeroth vector, because all its coordinates are 0. Now to show the second condition, we have to show that, so the first condition is satisfied. The second condition of a mapping being a norm, we have to show that the norm of lambda x infinity is equal to absolute value of lambda times the norm of x infinity. And in order to do that, we are doing the following. Let's look at the definition of this. Norm of lambda x infinity, this is the maximum of the absolute value of lambda xi when I is equal from 1 to n. This is by definition. We know that absolute value is these are now numbers, so we can write as a maximum of absolute value of lambda times absolute value of xi. I is equal from 1 to n. And because absolute value of lambda is a positive number, this can get in front of the maximum. So this is absolute value of lambda times maximum. I is equal from 1 to n of absolute value of xi. And this is exactly the norm of x infinity. So what we shown that this by definition was the norm of lambda x infinity. We showed that the infinity norm of lambda x is equal to absolute value of lambda times the infinity norm of x, because this by definition is the infinity norm of x. So the second condition is satisfied. Now to show the third condition. Third condition was the triangle inequality. In order to show the triangle inequality, let's first use the fact that xi plus yi, which is a triangle inequality between numbers, is less than or equal to absolute value of xi plus absolute value of yi. Xi is a fixed coordinate of your vector, and therefore absolute value of xi is less than or equal to the maximum of the absolute values of all coordinates xj over all j from 1 to n, and absolute value of yi is less than or equal to the maximum of the absolute value of yj for all j from 1 to n. Because this is one instance, and here is the maximum over all instances. And so this last one, by definition, this is the norm of x, the infinity norm of x. And by definition, this is the norm of y. So what we have shown, if we look at the first inequality, the first part of the inequality and the last part of the inequality, what we have shown is the following, that for every I, absolute value of xi plus yi is less than or equal to the norm of x infinity plus the norm of y infinity. And this is true for all I from 1 to n. Well, if something is true for all I from 1 to n, then it will be true for the maximum of it. So therefore, the maximum over I from 1 to n of absolute value of xi plus yi is less than or equal to the norm of x infinity plus norm of y infinity, because here this right-hand side does not depend on y. It's some fixed constant that does not depend on y. And here for every y, we have that this constant is an upper bound, and therefore this constant will be an upper bound for the maximum among all the y's. But then this is exactly the definition of the infinity norm of x plus y. So what we get is that the infinity norm of x plus y is less than or equal to the infinity norm of x plus the infinity norm of y. And this is exactly the triangle inequality, or the third condition for a mapping to be norm. And therefore, we show that the mapping that is defined this way is indeed a norm. So to go back to where we left the my slide, all those have to be shown that they are norms. We show only that the infinity, this is a norm. We went through the proof, but in general, one has to show that all these mappings are a norm. And if we would like to look at the closed balls for these norms, what is happening is the following. So we'll do the picture in R2. What is the closed L infinity ball, unit ball? This is the set of all vectors in R2 for which the infinity norm of x is less than or equal to 1. So what does that mean? That means that the maximum between the absolute value of x1 and the absolute value of x2 is less than or equal to 1. Well, the maximum is less than or equal to 1 if and only if for each of them x1 is less than or equal to 1 and x2 is less than or equal to 1. So what do we have? This is together, so this is considered as a system. So if here we plot x1 and if here we plot x2, so what do we have? We have x1 between -1 and 1. It lives in this strip here. And then we have x2 between -1 and 1. So x2 lives in this strip here. And therefore, we end up with the square because it has to belong to the intersection. We end up with this square that is -1, 1. And then here is -1, 1. Now, when we talk about the unit ball for the L2 norm, this is the set of all x's for which the norm of x2 is less than or equal to 1, but the 2 norm of x is the square root or absolute value of x1 squared. Since we are in the real, we can forget about the absolute value. X1 squared plus x2 squared to power 1/2 is less than or equal to 1, which means that x1 squared plus x2 squared is less than or equal to 1. And this is exactly the circle with center 0. My circle doesn't look like a circle, but this is the circle with the center 0. And this is the unit ball for the L2 norm. So these are all the vectors whose magnitude is less than or equal to 1 with respect to the L2 norm. And then what will be the L1 ball? The L1 ball is the set of all x's for which the 1 norm of x is less than or equal to 1, which is 1 norm of x is absolute value of x1 plus absolute value of x2 is less than or equal to 1. Which basically, if you write down this, it will turn out that this is a cube, and this cube is goes this way. So this is one line here, the second line here, here, and here. This is the unit ball of L1. So if you look at this norm, the P norm for P between 1 and 2, the unit ball is contained, is bigger, is a convex body that is containing this square, but is contained in the circle. So this is a unit ball for P between 1 and 2 for the LP norm of X. And when P is bigger than 2, then what we have when P is bigger than 2, when P is bigger than 2, then the unit ball is a convex body that is contained the circle, but is contained in the bigger square. So this is the unit ball for the it's centrally symmetric. The unit ball for the LP when P is bigger. So for P bigger than 2 and less than infinity. As P grows, this green ball is getting closer and closer to the square. Okay, so now we have new spaces that we're going to consider. These spaces are the LP spaces, and these are they are given by an index P that is here in the integral, and they are given by the domain of the functions that it consists of. So these functions are defined on the interval AB. So LP is the space of all measurable functions defined on the interval AB. And actually, as I mentioned before, these are equivalence classes, such that the integral of A to B of absolute value of f of x to power p, absolute value of f of x to power p dx is less than infinity. And this is defined for p between 1 and bigger than or equal to 1 and less than infinity. And when p is equal to infinity, there is a space called L infinity. And this is the set of all functions that are measurable and defined on the interval AB. And actually, this is the set of all equivalence classes of functions, which are bounded almost everywhere. Also, we will consider the set of all functions, which will denote by CAB. And these are the set of all functions defined on the interval AB, taking real values, and they are continuous functions on the interval AB. So for each of these sets, we can, which are vector spaces, we can define norm. So the L1 LB norm is of a function f, or equivalence class f, that belongs to L1 AB, is defined by integral from A to B of absolute value of x dx. So let me remind you what was the L1 norm for x1 and so on, vector xn. The L1 norm of this vector was the sum. So this was sum of absolute value of xi. I is equal from 1 to n. So think that the sum in the continuous case, the sum is substituted by the integral, and then the absolute value of xi is substituted by the absolute value of f of x. Now, if we look at the norm in the space L2, then this is the integral from A to B of f of x to power 2 dx, and then everything raised to power 1/2. This norm is the norm that is given by the inner product. You remember that in L2 we have inner product, that if we have two functions or equivalence classes f and g, then the inner product was given of f times g bar, f of x times g bar of x dx. And therefore, if you look at that, if you look at f inner product with itself, then this will be integral from A to B of f of x, and then absolute value complex conjugate f of x dx, which, since these are complex numbers, is absolute value of f of x squared. And then we know that the norm would be then the square root of f inner product with itself. So it will be square root of integral from A to B of absolute value of f of x squared dx, which is exactly what we have here. So the L2 norm, this L2 norm is actually the L2 norm induced by the inner product. And if you look at the, you look at the discrete case, then what was the L2 norm? That was the sum of xi absolute value squared, I equals from 1 to n, and this raised to power 1/2. Again, the power here is the same. The integral, the sum is substituted by the integral, And then we have the sum of the coordinates, absolute value of the coordinate squared. And here we have the function absolute value squared. And in general, the LP norm for P between 1 and infinity, here instead of 2, you will have P for the LP norm. So you have integral from A to B. You will have the absolute value of the function to power P. Dx, so you compute this integral and then you raise it to power 1 over p. And if we look at the corresponding discrete case, then the LP norm in this case was the sum I equals from 1 to n of the absolute value of xi to power p, and then everything raised to power 1 over p. So again, 1 over p, outer power 1 over p is the same. Then the sum here transforms to integral into the continuous case, and absolute value of xi, this is the absolute value of f of x, and then the p power is the same. Now, what is the L infinity norm? The L infinity norm is basically the infimum over all constants C, such that the absolute value of f of x is less than or equal to C for almost all x in the interval AB. So how do we explain this? And how do we see that this is related to the case of to the discrete case? So if we, for example, look at the interval AB, and let's look at this function, which is everywhere constant, then at some point here, it jumps up, and then it is the same constant. So here it is empty. At this point jumps up, and then it continues until the end. Let's say here is 1, and let's say here the value is 100. So what will be the L infinity norm of such a function? According to the definition, this is the smallest constant, such that the function is less than or equal to this constant for almost all x in AB. Well, the infinity norm then, the L infinity norm then of this function will be 1, because the only place where f of x is not going to be less than or equal to 1 is at this point here, at which it will have value 100, but it is doesn't matter, because we would like this to happen for almost every, the inequality to be for almost every x. So if we have, for example, a finite number, which is a particular case, but if we have a finite number of points at which my function takes some crazy values, or is takes values that are not in this set, then this would be okay. Still, the infinity norm will be 1. So the smallest c for which the function is bounded from above by this c for almost all x. That means it does not. It is not bounded by C for x that are x of that make a set of measures 0. And then if we look at maybe this will be visualized with CAB norm, which is the following. We know that if a function is continuous and if it is defined on a closed interval, then this function attains its minimum and maximum value. So the infinity norm of the C norm of a function f is the maximum of the absolute value of f of x when x belongs to the interval AB, which we can associate with if we have the discrete case of vector x, then the infinity norm of the vector x, this is the maximum of the absolute value of xi over all coordinates xi. So we have maximum and we have maximum. Here is maximum of the absolute value of all components of our vector, and here we have maximum of the absolute value of all function of the maximum of the absolute value of the all function values when these function values run through the domain, when x, the argument runs through the domain of the function. So these are the counterparts of the norms that we discussed before in the discrete case, and these are their counterparts in the continuous case when we're dealing with functions. Then there are various inequalities between vector norms. For example, we have this inequality between the 1 norm and the 2 norm and the infinity norm. For example, if we have the 1 norm, which is absolute value of x1 plus and so on plus absolute value of xn. x1 is less than or equal to the maximum of all absolute values xi, plus and so on. All these are less than or equal to the maximum of the absolute value of xi. But the maximum of the absolute value of xi, this is norm of x infinity plus and so on plus norm of x infinity. And so this is equal to n times norm of x infinity. So what we showed here is that the 1 norm of x is less than or equal to n times the infinity norm of x. And then what also we can show is that the infinity norm of x is the maximum of absolute value of xi. But this maximum, since it is running over a finite number of instances, this maximum is achieved for some xi0, and therefore is less than or equal to the sum of the absolute values of all the x's, because xi0 is somewhere here in this sum. And then this is equal exactly to the 1 norm of my x. So what we have is that the infinity norm is less than or equal to the 1 norm of the 1 norm is bigger than or equal to. So this is what we showed, that the 1 norm is bigger than or equal to the infinity norm. Okay, so if we look carefully in this inequality, it shows us that there are 2 constants, the constant 1 and the constant n. You see here that this constant n depends on the dimension of the space, because this is for the space Cn or Rn, that is of dimension n, such that for every element in this space, 1 times the infinity norm of x is less than or equal to the 1 norm of x is less than or equal to the constant n times the infinity norm of x. And according to our definition of equivalent norms, which was somewhere here, 2 norms are equivalent exactly if they are 2 constants, such that if you apply the norm, 1 norm, to an element x, you can bound from above and below this n1 norm with the n2 norm of the element within within 2 constants. And this is what we showed here. We showed that the infinity norm and the 1 norm are equivalent, and we found explicitly the constants which actually give us this equivalence. This is in agreement with the fact, with the theorem, that every 2 norms in a finite dimensional vector space, and here Cn or Rn are finite dimensional vector spaces, any 2 norms are equivalent. And for example, if we would like to prove this inequality, we will prove, we can prove a little bit a different version. Let's say we have integral from a to b of absolute value of f of x dx. This is the L1 norm of the function f. So this is the L1 norm of the function f. This is less than or equal if we look at the maximum of f. So this is less than or equal to the maximum of f of x over the whole interval. So this will be the infinity norm, the C norm of f on the interval AB, because this is a bound. Remember that the C norm of f is the maximum of f of x, and therefore for every x in the interval AB, we will have that f of x in absolute value will be less than or equal to its maximum, which will be less than or equal to the infinity, to the C norm of the function f. So we come here. So we have that f of x is less than or equal to the C norm times 1 dx, but this is a constant. So this can be put out. So this is the norm of f CAB. And then we have integral from a to b of 1 dx, which is x in the interval AB. So this is integral from a to b of 1 dx. And this is equal to the norm of f C on AB, and this is times x in the interval AB. So this is b minus a, which is the same as this. The only difference is that this inequality is also true not only for the C norm, but this inequality can be used also for the infinity norm of AB, because it is true for almost everywhere. And when you integrate, you don't care about sets of measure 0. Now, there are a few inequalities that are important inequalities for norms, and these are the Hölder inequality and the Cauchy inequality, which is a particular case of Hölder inequality. So if you have P and Q, which are two numbers between 1 and infinity, including 1 and infinity, even though you may not say that infinity is a number, but and then if you have that 1 over p plus 1 over q is equal to 1, then the inner absolute value of the inner product of x and y is bounded from above by the p norm of x times the q norm of y. And this inequality has its counterpart. So this is the inequality for Cn or Rn. And this inequality has a counterpart in the set of functions, the spaces that we discussed. So the inner product between f and g is integral of from a to b of absolute value of f of x dx. This is the inner product of f and g. Well, the inner product between f and g, let's do the following. Let's look at the functions f and g, which are from the interval AB, and which take real values, so that we do not worry about the complex conjugation. So we take two functions f and g that are real valued, and then we know that the inner product of those two functions, this is f of x. I should put g bar, but because they are real valued, is g of x dx. And absolute value of the inner product is this. But then this is less than or equal to, I can put the absolute value inside. So I have absolute value of f of x times g of x dx. And then this is less than or equal to integral from a to b of f of x to power p, everything to power 1 over p, times, which is the p norm of f. This is the p norm of f, and this is the q norm of g. And in particular, this is also the, in the case when p is equal to q is equal to 2, this turns into so-called Cauchy-Schwarz inequality, which tells you that integral from a to b of absolute value of f of x times g of x is less than or equal to the L2 norm of f times the L2 norm of g. Now, in particular, when q here is infinity, 1 over infinity is viewed as 0, and then p is equal to 1. So if we look at this inequality here, then what does it tell us? It tells us that integral from a to b of absolute value of f of x times g of x is less than or equal to the infinity norm of g. Right, because if q is equal to infinity, and times the L1 norm of f. So f, L1 norm of f. And if we look at what we were showing here, absolute value, the norm is integral, the L1 norm of f is integral from a to b of f of x, and I can view this as f of x times 1, and I can view this as the function that I applied the infinity norm. So I put the infinity norm on g here, but at a function to which I applied the infinity norm, so this will be less than or equal to the infinity norm of the function f, L infinity, times the 1 norm of the function 1. Well, the 1 norm of the function 1 is integral from a to b of 1 dx, and this will give you exactly the b minus a. So you can view this inequality as the Hölder inequality applied to the function f of x and the function 1. This is the norms for, we discussed so far norms and inner products for the space Rn, Cn, and all the spaces Lp, Ab. In what is left is to show that we can introduce those also for matrices. And the way to introduce this for matrices, actually the norms, is similar to the way people introduce it for linear operators. So first, if we look at the matrix A, which is matrix with n rows and n columns, the same thing that I'm going to talk about here can be done for non-square matrices in which the number of rows is different from the number of columns, but we will talk only about square matrices. So if I have a square matrix, I can take the elements on the first row, and then I can take the elements from the second row, put it next to the elements from the first row. So this is row 1, this is row 2, and so on. I can take the last row, and this way I can create a long n square dimensional vector, because I have n groups of each of n elements, n groups, each group is the row. So I'll have n square dimensional vector, and I can use then the notion of a norm of a vector in Cn squared to measure the size of A. This is done as we will see at the end of that particular subsection here, which is called, in some particular case, which is called the Frobenius norm, but we're not going to pursue that avenue. We will talk and investigate the norms of a matrix if we view the matrix as a linear operator. So we investigate the behavior of a matrix as an operator between its norm domain and range spaces. So what does that mean? If I have the matrix A, then let's say it is n times n, and let's say it is with real entries. Then if I look at the matrix A, this matrix can be viewed as a mapping from Rn to Rn, because to every vector x in Rn, I can associate the vector Ax. And therefore, I can have, since A is a matrix, this is an operator that is a linear operator. As in a linear operator, it has a norm. And I define the norm of a matrix as a norm of this linear operator, which I am doing right here. So what is the norm then of a matrix? If I go this way, it is the smallest number, so C, for which the norm of Ax is less than or equal C, the norm of X, for all X in Cn. Let's say A is from Cn to Cn. So what is this norm here? This is a norm of a vector. And therefore, the norm of a matrix that I define this way, the smallest C, will depend on the vector norm that I have selected here. That's why this norm is called an induced matrix norm, or a matrix norm that is subordinate to a particular vector norm. Or let me back up and say the following. I have in the space Cn, I have my favorite vector norm, which for every vector x in the space Cn assigns a number which is the norm of that vector. Then I look at the matrix A, I apply to the vector x. Once I apply to the vector x, I will end up with another vector in Cn. I can apply this particular norm to that vector. And then I would like to estimate how big will be the increment, how big will be the magnitude of this vector in comparison with the magnitude of the original vector x that I started with. So the smallest C, for which the norm of Ax is less than or equal to C, the norm of X for all X in C, is called the induced matrix norm. Equivalently, I can restate that as the following. The norm of the matrix A, which is induced by a corresponding vector norm, is the maximum factor by which A can stretch a vector X, or the formal definition is the sup of the norm of the vector Ax divided by the norm of the vector X when the sup is taken over all elements in Cn that are different from 0. Now, as we discussed before, if I look at that, so this is the sup. Now I have 1 over the norm of X times the norm of Ax. This I can put in. Here's the sup of all vectors in Cn, which are different from 0, which is the sup over all vectors X in Cn that are different from 0. And this is norm of 1 over the norm of X, A applied to the vector X. So now this is a number. This number can go between the matrix and the vector. So this is the sup of X is in Cn when X is different from 0. And this is the norm of A applied to the vector X over the norm of X. And we discussed before that X over the norm of X, the norm of this vector is 1. So when X moves and lives around Cn and is different from 0, that vector, let's call it Y, X over the norm of X, actually lives on the unit sphere because the norm of this vector is equal to 1, the unit sphere with respect to that vector norm. So then this sup is equal to the sup of the norm X over the norm of X now is the vector Y. And when X moves around in Cn, Y lives and moves around in Y. So this is the sup over all vectors Y, for which the norm is equal to 1, which is exactly this. So the definition can be viewed in two ways. You either divide the norm of AX by the norm of X, or you look at the norm of AX when X is restricted to live only on the unit sphere with respect to this vector norm. So this is how we can define an induced matrix norm that is associated with a particular vector norm. Now, if this vector norm here, is the one norm, then the corresponding induced matrix norm will be the one norm. So it will be one norm of A will be the, let's use the second definition, AX, the one norm, when the one norm of X is equal to 1. If we use the infinity norm, then we will end up with the induced infinity norm matrix norm of A, which will be the sup of the infinity norm of the vector AX when the sup is taken over all X for which the infinity norm of X is equal to 1. Or if we want to have the two norm, the induced two matrix norm, then this will be the sup over the norm of AX, which will be the two norm of AX divided by the two norm, not divided by, but the supremum is over all x's for which the two norm is equal to 1. So we put here the same index as we put here and here, and here and here and here and here. And then we defined, where was that? Yes, here I am showing. So here we define the one norm of A, or we can define the infinity norm of A, or we can define the two norm of A. We can define the two norm of A. Now the question is, before going into that road, to show the following important inequality, that if we have a norm, vector norm, and we have a corresponding induced matrix norm, then the norm of the vector AX is less than or equal to the norm of the matrix A times the norm of the vector X. And how do we prove that? Well, this follows directly from the definition of a norm of a matrix. If we look here, first of all, let's note that this is true. So let's prove this inequality. First, if when X is equal to 0, we have that the norm of X is 0. We have that A applied to X is A applied to 0, which is the 0 vector and is 0. And therefore here I will have 0 and here I will have 0. Since the norm of X is 0, and since the norm of AX is 0, I'll have 0 less than or equal to 0, which is correct. So let's say, consider the case when X is different from 0. If X is different from 0, then I look at the definition and I see that the norm of A is equal to the sup of the norm of AZ over the norm of Z, where the sup is taken over all Z in Cn, and Z are different from 0. But since it is the sup of this quantity over all Z's, and I'm taking a particular X, then the sup, or the biggest among those, will be bigger than the particular one that I'm taking. So this will be bigger than or equal to AX divided by the norm of X, and therefore I have the norm of A is bigger than or equal to the norm of AX divided by the norm of X. And therefore, if I multiply both sides by the norm of X, I have that the norm of X times the norm of A is bigger than or equal to the norm of AX, which is exactly this inequality, but written the opposite way. So it is written here backwards, and here it's the other way. So this is an important inequality. Another important inequality is that if we look at two matrices, and if we look at the norm, matrix norm induced by a vector norm, then the norm of AB is less than or equal the norm of A times the norm of B. And why is this? This follows directly again from the definition. So if we look at what we have here, we can prove it, but it will be to be done for one of your homework problems. And next time we will continue with discussing easy ways in which we actually can compute these norms, because if you look at the definition is not computationally friendly, because you have to compute the supremum. Here, this supremum is actually a maximum, because clearly it's a maximum because it is a continuous function over a compact set, and therefore you know that it is not easy to compute from the definition what the norm of your matrix is. And next time we will discuss what will be the ways in which we will compute, easy ways to compute the one norm of the matrix A, the infinity norm of the matrix A. So these are basically the only two norms that can be computed easily. We will discuss what the formula for the two norm of the matrix is, but we are not going to go that route. We'll just say what it is, but we're not gonna prove it. Okay, that is it for today, and until next time.